All right, so here we go with some more single variable calculus review. So this is going to be some further discussion of derivatives. And so here we're going to talk about differentiation formulas. So again, we're using the calculus book by Stewart for all of this. So all of the derivative formulas come from the limit definition of a derivative. So for example, after all of this time of knowing calculus, you might at this point take it for granted that this is equal to 0 for a constant c. But then do you remember why that's true? And so let's remind people how all of these formulas come about. They come about from the limit definitions of the derivatives. So for example, if f of x is equal to c, then let's use the limit definition of a derivative. So f prime of x is going to equal the limit as h is going to 0 of f of x plus h minus f of x over h by definition of the derivative. And so if we actually put this in here, we'll say f of x plus h, well, that's still c, because f of x or x plus h or anything is always c, and then f of x is also h. So this will be the limit as h goes to 0 of c minus c over h, which is equal to the limit as h goes to 0 of 0, which is equal to 0. And so, and then also you can think the reason even these are also true is coming from the precise definition of a limit. So that idea that for all epsilon greater than 0, so let me write this out. If this is true, if for all epsilon greater than 0, there exists a delta greater than 0 such that the c minus c over h minus 0 is less than epsilon whenever 0 is less than h minus 0 is less than delta. And so here, no matter how small I make the h here, I always get that this is less than epsilon because this is 0 whenever the h is not 0. And so I can always, no matter what epsilon I give, I can always make this just be 0. So as long as epsilon is greater than 0, for sure this is always satisfied no matter what h I've got. So therefore we meet the epsilon delta definition. So therefore this limit is equal to 0. And then we also demonstrate with this that from the definition of the derivative, that therefore the derivative of f of x equals c is also 0. So this is meant to be the reminder of like how these things come about, and that it's not really just like, oh, I learned a lot of rules in calculus class, but that now we kind of revise our understanding to remember it. So we can also look at some other things like d over dx. For example, x equals 1. This is also going to come from the definition of the limit definition of derivatives when your f of x is equal to x. We could do one where we have d over dx of x to the n is equal to n, x n minus 1. It's also interesting to look at the proof of this just as the second example, because in this case, this is one that we use quite a lot. So just so people again remember, something that is true by factoring, so this will look unrelated for a second, but it's going to come up in just a sec, is that you could demonstrate that this factorization is equivalent to x to the n minus a to the n. So it's x minus a times x to the n minus 2a plus dot 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 plus x a n minus 2 plus a n minus 1. And so here we have that if f of x is equal to x to the n, which would mean f of a is equal to a to the n, then let's look at the actual definition with limits of f prime at a. This is going to equal the limit as x goes to a of f of x minus f of a over x minus a, which is equal to the limit as x goes to a of then, we would plug this in here. So we plug in for f of x, we're going to plug in x to the n. For f of a, we're going to plug in a to the n minus a to the n over x minus a. And so then we can now use this thing where we factor out x minus a from the top. And then we'll see that this x minus a on top is going to cancel this one. And so we're going to end up with this as the limit as x goes to a of x to the n minus 1 plus x to the n minus 2a plus dot 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 plus x a to the n minus 2 plus a to the n minus 1. And so we already know that it can be proved from the fundamental definitions of limits that if f is a polynomial or a rational function, and a is in the domain of f, that then the limit as x goes to a of f of x is equal to f of a. So this is a little bit of abusive notation here, because here I'm talking about like a different f than what we had up here. This is just a general statement that we had, I think, in some prior lecture here. But then, so what this means is that now I'm going to be able to plug a in for this expression. So it's going to give me a to the n minus 1 plus a to the n minus 2 times a plus dot 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 plus a times a to the n minus 2 plus a to the n minus 1. And so we see that this becomes a to the n minus 1 for however many of these terms that we have here. So this is going to give us, since we're going to have n terms, because it goes from the 0th term up to the n minus 1th term, it's going to give us n times a to the n minus 1. So this is the formula that you know, but then now you will remember how we get it, and also remember that it is fundamentally tied to the limit definition. Okay, so this gives the idea there's no derivative in a table where you could not prove it from the limit definitions of the derivatives, assuming those proofs are easy enough, or from something derived from that. So then really quick, just so everybody remembers all this stuff, if c is a constant and f is a differentiable function so that we can actually get the derivatives, then we're going to have that this is true. It is important that f is differentiable here and c is a constant. Mostly I want to state this because I think it's important that people start getting used to the idea that the caveats that are mentioned actually do matter, because the results no longer follow. For example, this definitely is not true if f is not differentiable, because then what does it mean to take df dx? And then here we have that if both f and g are differentiable, then we have those different properties that probably people remember, like for example, this one that expresses linearity of differentiation, so that we can, if we have a sum of two terms, then we just sum their derivatives. Then we also can say, oh, what if I have a subtraction of two terms? Then we're going to get the subtraction of these terms. And then, oh, what if I have the derivative of the product? So then there's the product rule. And then this one is going to be that it's f d over dx g of x plus g of x d over dx f of x. And then also the quotient rule, where this is going to equal g of x d over dx f of x minus f d over dx g of x, and then over g of x squared. Usually I like to try to make things into the product rule, because I find that one much easier to remember by, like, if I have something that's in the denominator, just making it like g to the -1 and stuff like that. Okay, and then so if people want to say, well, why are the product and quotient rules? Can you also demonstrate that those come from the limit definition of the derivative? So really quickly, let's just review to show, like, yes, you can also demonstrate that all of these come from the fundamental definitions. So let's say let f of x be equal to f of x g of x. Then the derivative of this, f prime of x, is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. This is just the definition of the derivative, and then we can start plugging in for f. So we'd say, oh, okay, this is equal to the limit as h goes to 0 of here. I'm going to put f of x g of x because that's what we have, minus plus h, and this one plus h, and then minus here we have f of x and g of x over h, and then in this case, then this is going to equal the limit as h goes to 0. We're going to do that thing where we add and subtract the same number because that's part of a lot of proofs of stuff. But now we have to say, what are we going to add and subtract? So we're going to subtract something where one of them has an x plus h and one of them only has an x. And so let's take this one. And this is going to allow us to pull out the f of x plus h from this term. And then in the next term, it's going to allow us to pull out the g of x. So then we're going to add this back so that effectively overall we add 0. And then we have like this over h. And then this is then going to equal the limit as h goes to 0 of f of x plus h, and then times g of x plus h minus g of x over h plus g of x times f of x plus h minus f of x over h. And then assuming that the limits of these different functions exist, we can start going back to the limit laws and saying like, oh, okay, well, this is going to equal the limit as h goes to 0. Okay, I'm going to split these two terms up. And so this will be if I have x plus h on its own. I'm also going to split up their multiples. So the limit as h goes to 0 of g of x plus h minus g of x over h plus, and then I'm going to do the limit on the second set of terms, g of x times the limit as h goes to 0 of f of x plus h minus f of x over h. And so then we can say, oh, look, how interesting. This is actually the definition of the derivative of g. This is the definition of the derivative of f. And so, and also in this one, if I let h go to 0, then assuming that f is continuous at x, so that I'm able to plug in the h is 0 here, and then we consider that f is continuous at x because it's differentiable at x, I'm going to end up with f of x times g prime of x plus g of x times f prime of x. So then now you can even see that even our product rule, for example, and therefore also all the other ones, is going to follow from the definition of limits, so that again, these are not just like, oh, isn't that cool that someone knows that that's true and very useful to me to apply in problems, but now you can even prove these properties and that they exist and understand more deeply where they all come from. Okay, then other stuff, just so everybody remembers, because these are really common ones. People probably remember these, but sometimes it's helpful to just see which ones I believe are common. So if n is a positive integer, then we get that d over dx of x to the negative n is equal to negative nx to the negative n minus 1. We're also going to get that x is a real number. Then we're going to get what we already showed, that x to the n is equal to nx to the n minus 1. We also can get our derivatives of all of our sine, cosine, etc. functions. So the derivative of sine is cosine. The derivative of cosine is negative sine. We also have that the derivative of tan is secant squared. The derivative of cosecant is negative cosecant. Oh, sorry, what that wrong one? Negative CSCX cotangent x. The derivative of secant is secant x tangent x, and the derivative of cotangent x is equal to negative cosecant squared of x. And then remember, if you ask yourself, wow, some of those I haven't seen in a long time, I wonder how someone knows those. The answer is they know them because they applied the fundamental definition of the limit and they discovered that this was true. And so there you go. So that should hopefully bring that back and also remind people of the fundamental perspective there, that it's not just, oh, I have a table, but that the everything that we are learning, you can actually prove this stuff and it comes come forth from that. So now let's go over the chain rule. So the chain rule here, for those who may have forgotten, so we have f of x is equal to the square root of x squared plus 1. And then if we have y is equal to f of u is equal to root u in this case, so then you can see that this would be a composition of functions. If we let u equal g of x is equal to x squared plus 1, then we have that y is equal to this f of x is equal to f of g of x. And so this is the function composition. So this is equal to f composition g. Okay, so the chain rule, this says that if both f and g are differentiable, so the caveat, they do have to be differentiable or else this isn't going to work, and f equals f composition g is the composite function defined by f of x is equal to f of g of x, then f is differentiable and f prime is given by f prime of x is equal to f prime g of x, g prime of x. And so in the Leibniz notation, if we were to write this as like y equals f of u and u equals g of x are both differentiable functions, then dy over dx is equal to dy over du over dx. And so just remember though that these are not actually like intended to be quotients here. We're like, oh, look, the du's, they cancel out, and so it gives me back dy dx. That's not what's going on with this. But this is a helpful like notation for helping remember it. Okay, so then you can say, oh, wow, the chain rule is so interesting. It's so interesting that people figured that out. Okay, well, can you prove it? So then now, let me check if I actually wrote the full proof of the chain rule out. I think I do have it here. So let's look really quick at the proof for the chain rule. So let's say if y is equal to f of x, and actually I'm not going to write the whole proof of the chain rule, but I guess the important point is that you can prove it, and a lot of times writing the proof will give you a deeper insight. What I'm going to do instead of actually writing the proof of the chain rule is I'm going to demonstrate a use of it. So let's say find f prime of x for f of x is equal to root x squared plus 1. And then, so in this case, we want to think about the type of notation we were just looking at. So we need to define like essentially our f and g. Or you could think of it as defining your g of x and your f of u is your y. And so I'm going to go with the second notation. Well, I'm going to show it both ways. Let's say that we use the first notation. So we have f of x is equal to f of g of x is equal to y. And then in this case, we would say that u is equal to g of x and that the f of u is equal to y. So what this would give is that the f of g of x is equal to y. And then we also have that we could write it as u equals x squared plus 1, where f of u is equal to root of u. And then this would give us that like f of root x squared plus 1 is going to be like that. So in this case, both the f and the g are differentiable, so we're good. And so we can get f prime of x is equal to what we have up here, right? So it says f prime of g of x times g prime of x. So is equal to f prime g of x times g prime of x. So in this case, we would get the derivative of f with respect to its independent variable and then plug in g of x, and then the derivative of g with respect to its independent variable. So we're going to say df over du is equal, in this case, to, using this one, 1/2 u to the negative 1/2. So it's equal to 1 over 2 root u. So this is df over du. And then we can also do the dg with respect to its independent variable, which is x. So it's equal to 2x. So then if we write f prime of g of x, this means that we take the df du and we have to plug in g of x into it. So it's going to be 1 over 2 root, and then the g of x here is going to correspond to the x squared plus 1. And then if we have f prime of x now is equal to, it's this first part f prime g of x times this other part dg dx. So it's going to give us 1 over 2 root x squared plus 1 times 2x. And so this is going to end up as x over root x squared plus 1. So that's one way if you want to do it with the f primes. And then the other way, if it helps you think of it, is if you do dy over dx is equal to dy over du times du over dx. So then in this case, you would say, okay, well, dy over du is going to be the same part, 1 over 2 root u, and then times the du dx, which is equal to 2x. And then so it gives the same thing, because then you plug in your u is equal to x squared plus 1. So 2 root x squared plus 1 times 2x. And there you go. So for anyone who forgot about this, now remind yourself of the chain rule so that you do it in the correct way, because it's very important for getting correct answers. Okay. So if n is a real number and u equals g of x is differentiable, you could prove that d over dx of u to the n is equal to n u to the n minus 1 times du over dx for your chain rule. Okay, and then there's also some other interesting stuff that you can prove. And then if there are multiple instances, you would use the chain rule multiple times. So like, for example, say y equals f of u, and then u equals g of x, and then we have x equals h of t, and then the f, g, and h are differentiable. Then if we want to get dy over dt, we're going to have to use the chain rule twice. So we'd have dy over dx times dx over dt. And then we'd say like, oh, well, you know, the dx over dt, I also have to split dy over dx further. Then, so dy is actually a function of u, but u is a function of x. And then x is a function of t, so etc. So like, for example, if you want to see something really, really weird and see like, oh, wow, this actually could be very useful to me in some cases when, like, for example, this if I first think about this, I'm like, oh, wow, I haven't seen like a derivative that hard in a long time, right? So then let's think about how we would do this with the chain rule. So we would say, okay, y equals sine u. Then you can say, okay, and u equals cosine of x, and x is equal to tangent t. And this makes it seem actually not so bad at all, because this makes it be that dy over du, du dx, and dx dt is going to equal the dy dt for this. And so then it's like, oh, okay, no problem. So now dy with respect to u, so it's just going to be cosine of u. And then this next one, du dx, so then I get negative sine of x. And then the last one is the derivative of x with respect to t, so it's going to be secant squared t. And then if you plug in the different parts here, so then you say, okay, so I get negative cosine, so u is equal to cosine of tangent t. And then I have negative sine of tangent t, and then secant squared t. So if you're like, wow, I really have not seen some like derivative that complex in a long time, well, now you remember how to do it. So good. Okay. Then implicit differentiation. This is if you're going to differentiate both sides of an equation with respect to x and solve the resulting thing for dy dx. So like x squared plus y squared is equal to 25, and you want to get dy over dx. Then you say like, oh, okay, well, I differentiate this first thing with respect to x, so good for me. And then the second thing, y is a function of x, so I can do 2y dy dx is equal to 0, and then I can solve for dy dx is equal to negative x over y. So this would be implicit differentiation. Then you would do this, you would know like the way to get this, for example, from the chain rule that we just did. But then what else have we got here? So then we have infinite limits. So what happens if it says there are limits going to infinity? So first thing we have to do is to define what does it mean for a limit to be going to infinity. So let f be a function defined on some interval from a to infinity. Then the limit as x goes to infinity of f of x equals L means that for every epsilon greater than 0, there exists n such that f of x minus L is less than epsilon whenever x is greater than n. So then we have to break this down a little and say, okay, what's that trying to communicate to me? So it's trying to say that I have a function and it's defined from some number to infinity or its domain includes some number to infinity. Then the limit as x goes to L, or the limit as x goes to infinity of fx is L means that whenever or for any epsilon, f of x minus L is less than that epsilon whenever I get x greater than n. So it's expressing that I can, essentially I can make f of x arbitrarily close to L by making x as big as I want. And so that's the idea with this. And then similarly, if you want to do it for like negative infinity, then there would be a similar idea, but you'd be looking at cases where x is less than a number, for example. This would be cases like if r is greater than 0 is a rational number, then we have that the limit as x goes to infinity of 1 over x to the r is equal to 0. And then so you could say, well, how do I know that, on what basis? And then you would say, well, for this function, as I make the x arbitrarily large, what value is my 1 over x to the r approaching any value? And so I say, like, yeah, as I make the x to the r arbitrarily large, I can see that this is becoming closer and closer and closer to 0. And so then that gives you a sense of why that one would become 0. And then yeah, and you would get a similar thing if it was going to negative infinity. You would also say a similar thing, like, oh yeah, as I make this more and more and more negative, I'm also gradually approaching 0. So that same idea. And then, so with this is where we get some things like the limit as x goes to infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. And then, so here I could divide the numerator and the denominator by the highest power of x. So I could divide them both by x squared. And so then I will get that we're looking at the limit as x goes to infinity of 3 minus 1 over x minus 2 over x squared. And then I could do the similar thing here. So of 5 plus 4 over x plus 1 over x squared. And then you could apply your limit laws here. And in the end, this is going to equal 3/5, because the limit of this term and this term are 0, and the limit of this term and this term are 0 by this. And then so it just becomes 3/5. But then if you want to say, like, oh, well, how do I know that that's true? Then that would come from these types of questions. So like the fact that we're distributing things like this limit as x goes to infinity into the numerator and the denominator and stuff, that should come from going back to the use of the limit laws. So that we would be able to demonstrate that, like, for example, for the sum law, it would be, let the epsilon be greater than 0, then we must find n such that f of x plus g of x minus, sorry, these are x's, and that's an f, minus L plus M is less than epsilon whenever x is greater than n. If we wanted the sum law to be able to be used with these infinite limits. And then, so then you could go through this and you could demonstrate, you could say, like, okay, well, if f of x plus g of x minus L plus M is less than or equal to f of x minus L plus g of x minus M, similar to how we did it before, then if the f of x minus L is less than epsilon over 2 when x is greater than n, and g of x minus M is less than epsilon over 2 for x greater than n, then we would get that f of x plus g of x minus L plus M is less than epsilon for x greater than n. So then this would mean that the limit as x goes to infinity of f of x plus g of x is equal to L plus M. And so then you would be able to go through and do all the, like, and do other limit laws and see whether or not they continue to hold in this case with the infinite limit. But then that's the idea, is that, for example, if we're going here and we're saying, like, oh, I'm going to look at this by saying that this limit as x goes to infinity, I'm going to apply limit laws, and I'm going to say, for example, that, oh, I'm going to split this between the limit of the top and the limit of the bottom, and then distribute the limits between the different terms. The only way you're able to do that is if you actually make sure that the limit laws still hold when you have limits going to infinity. And then, so that's what I'm trying to show here, is this idea that For example, I could demonstrate that the sum law will still hold in such a case because I can say what would need to happen, and then I can say, can I find a delta for every epsilon? And then we can say like, or sorry, not a delta for every epsilon. In that case, for every time that we get x greater than n, or for every epsilon, can I find an n such that when x is greater than that n, that then like f of x plus g of x minus L plus m is less than epsilon. And so if I can find these n's every time, then I can demonstrate that the limit as x goes to infinity of this sum has to equal the L plus m. And so that's the idea for this. And then also, if we want to use the definition of a limit to prove, for example, that the limit as x goes to infinity of 1 over x is equal to 0, then that would again come from doing something like, given epsilon is greater than 0, we want n such that 1 over x minus 0 is less than epsilon whenever x is greater than n. And then, so that's what we want to prove. So then now that we say, okay, this is what I want to demonstrate to be able to demonstrate that this limit is true. Now let's try to say, oh, can I achieve that at any point? So the way that we would do that is we would say like, okay, let's say for a second that we take the case that x is greater than 0, because here the x is greater than n, so this should hold including when x is greater than 0. So let's have then that 1 minus x minus 0 is equal to 1 over x, which if x is greater than 0 is 1 over x without the absolute value. So therefore, I want, in order to prove this limit, to find that 1 over x is less than epsilon whenever x is greater than n. Or I could rewrite this as that 1 over epsilon is less than x. So x is greater than 1 over epsilon whenever x is greater than n. So what this suggests is that maybe if I say, oh, this and this kind of look like they're related. So maybe I should say, okay, let me try a proof where I say, what if n is 1 over epsilon? Because I knew what I wanted to achieve. Then I said like, okay, let's make some conditions and try to figure out how I might get there. It looks like maybe if I choose n is 1 over epsilon, like I could probably make this proof work. So then now that we did the sort of upfront figuring, then we can say that given epsilon greater than 0, choose n equals 1 over epsilon. And then we want to say, let x be greater than this number. And so you can see here that as epsilon becomes like really small, then as epsilon gets smaller, then a smaller value of epsilon will lead me to a larger value of n, and so forth. So if like epsilon is 0.1 versus 0.001, the n will be bigger when the epsilon is smaller. And so then we have that 1 over x minus 0 is equal to 1 over x, which is less than 1 over n because of this statement, which is equal to epsilon from this. So this means that we demonstrate that the 1 over x minus 0 is less than epsilon whenever x is greater than n. So by definition, then this has to be true. So that's the idea there. And then there's a few more final things I wanted to say about some precise definitions. So the definitions of limits at infinity. So infinite limits at infinity. And just to make sure people feel clear on what this is talking about when you see this, so this says let f be a function defined on some interval a to infinity, then we have that the limit as x goes to infinity of f of x is equal to infinity, means that for all m greater than 0, there exists a corresponding positive number, n greater than 0, such that f of x being greater than m, or f of x is greater than m whenever x is greater than n. And there'll be something like similar but different for negative infinity. So this indicates that f of x becomes large as x becomes large. And so, for example, if we say the limit as x goes to infinity of x cubed is equal to infinity, then the idea is that for all m greater than 0, there exists n greater than 0, such that x cubed is greater than m whenever x is greater than n. And I think we would agree with this, that the x cubed is getting arbitrarily large. So no matter how big I set the m here, then there's always some n, such that whenever the x is greater than that, I can make x cubed greater than my number. So this then has the infinite limit at infinity. And then if you look at an alternative case, it's like, let's say we look at this x squared minus x. So this is non-obvious because it's sort of like, well, the x squared looks like it's going to be like there's like this x squared and there's a subtracting, and so maybe it's not as obvious right away. And so you can't use the limit laws here if the limit of the terms is infinite, because that means the limits don't exist. So you can't just say like, oh, well, the limit of the first term is infinity and the limit of the second term is infinity, because what does that even mean? So infinity minus infinity, like, is that what you're saying? Like, you know, it's kind of like unclear what someone's trying to do. But instead of doing it that way, because the limit laws don't apply here because the limits aren't existing, instead what you can do is you can factor and say like, oh, okay, like, let's look at this. So we know that this term and this term are both going to be becoming arbitrarily large as I make x bigger. So what that means is that then their product must also be becoming arbitrarily large. So this means that for all m greater than 0, there exists n greater than 0 such that x times x minus 1 is greater than m whenever x is greater than n. So if x is greater than a certain number, we can see that the product of x and x minus 1 will get large. And so this is a more obvious form than when it was written like this, where it seemed like we're having like one large number subtracting another large number as the two numbers get large. Here we're able to see more clearly what the limit is because we're able to break it up in a way where we say like, okay, if this is a very large number minus 1 times the same like very large number, then whenever I make the x bigger than a certain, or I can make the x bigger than a certain amount such that no matter how big I would like this x times x minus 1, I can always make x bigger than a certain amount to get the x times x minus 1 greater than a certain number that I can specify. And so that concludes the discussion of everything before antiderivatives start. So before the discussion where it starts getting into integration, and that's the high level review of all of that.